Yeah.
So our next speaker is Alok Laddha. He's going to talk about towards the positive geometry of the mass.
Is it on? Yeah. So okay, let me start by thanking the organizers for giving me a chance to speak here and also visit Vienna for the first time. So this is the title of my talk, and almost everything I will say is based on work with Mrunmayee Jagdale, who is a graduate student at Caltech. But really what we do is, sort of a minor upgrade on a lot of large body of work which has been done in this, under the name of the Amplitude Hedron program for maybe last 15 years, as well as very seminal results in last 5 years by the many physicists, which are all indicated in red, and many mathematicians, and some of the names are indicated in blue. So let me start with some brief motivation, since this is the first talk on positive geometries. So we know that S matrix in quantum field theory come in many avatars. For example, there's the standard off-shell formulation where we start with the Lagrangian and do the Feynman diagram matrix and do LSZ formulation. But then since mid-90s maybe, or maybe early 2000s, we know that there are on-shell recursion relations where we never have to go off-shell and never have to use the local field description. There is the S matrix formulation in twistor space for a class of theories, especially supersymmetric theories. And there is also this beautiful worldsheet formula for generic quantum field theory, which is known as the CHY formula, which was discovered in 10 years back. So let me just briefly say what are the sort of postulates that underlie all these different approaches. So in the standard, off-shell approach, we know that unitarity and locality is manifest at every step in the computation, but there's a price to pay, and there is a very intricate and kind of almost out of control analytic structure, because you get singularities which are not only predicted by unitarity, but we get pseudo and anomalous thresholds and more complicated singularities. But if you do on-shell recursion relation, the postulates you use, you only use unitarity and the fact that you have some simple pole structure at tree level. And the price you pay is that locality is only emergent in the final step, and you don't really see locality at every step of the computation. And when you do this worldsheet formulation or CHY formula, I shouldn't really say postulate, but a key ingredient is what are called scattering equations, which tell you that you integrate some forms only on solutions of certain equations. And in this approach, what is remarkable is both unitarity and locality are really emergent due to the geometry of the worldsheet moduli space. So we see that in general, if different representatives sacrifice different postulates, then perhaps all of them are derived from a deeper set of postulates. And this question has mystified even Hollywood, and you see lines like this in Hollywood that in some movies that no one can be told what the S matrix is, you just have to see it for yourself. So the real question we want to ask is, what are kind of the hard fundamental postulates underlying the S matrix program? And one way to ask this question, maybe more practical way, is when do you say that a function in the space of external momenta classify as a S matrix function or a scattering amplitude? So this entire program has a lot of goals, but just for the purpose of this talk, I would just like you to keep this sort of a goal or a dream in mind, that one of the goals is to discover this deeper kind of set of postulates and seek a more sort of fundamental representation of the S matrix in which all the I should have said from which all the older postulates are derived, and not really, we don't assume the older postulates. So that's the goal that I would like you to keep in mind for the rest of the talk. So, and just want to say that the star of the show is going to be a specific class of geometries, which are called positive geometries. It has a much more nuanced definition, but I'm just giving you a very sort of sketchy definition that it's a geometry which has boundaries of all codimensions. So one example that you can keep in mind, you just take a line segment with two ends. So it qualifies as a positive geometry, but if you take I should say a disk. If you take a disk or even a circle, actually it does not, because it does not have boundary of, the lowest possible codimension, so highest possible codimension. So now the one message that I would like you to sort of take away from this talk is that hopefully is that locating positive geometries in the region of, external data or Mandelstam invariants leads to the S matrix integrand for tree level, we just get a S matrix, but in the higher one loop case, for example, we get some integrand for a large class of local and unitary scalar quantum field theory. So these things are just come out once we start finding some geometrical objects in the space of Mandel's terms. So that would be hopefully the main message of this talk. So we don't want to start with any postulates, but we have to start with something. So we start with some kind of elementary topological observations that we learn in quantum field theory that, whenever we compute S matrix, we always, perturbative S matrix, we start with Feynman diagrams. And you can see that if you take any tree level Feynman diagram, let's say with cubic vertices to begin with, then it's always dual to triangulation of an n-gon. So this is a simple picture. So this is kind of an obvious thing, but in fact, this is quite surprisingly, maybe it's also true at the loop level in the sense that you can take a one loop planar Feynman graph with say cubic vertices, and you can see that it's dual to triangulations, but these triangles are not always linear. They are technically what are called pseudo triangulations, and one way to represent it is the following. So if you take, for example, a 3-point Feynman graph with one loop with cubic vertices, then you can immediately see that it's dual. All the propagators are dual to these black lines. And this looks a bit complicated, but you can draw it more easily by kind of unfolding this triangle, making it like a hexagon. So it's like two copies of triangle. And then you can see that all these lines which are dual to the propagators, they all dissect this hexagon into triangles. But these are not linear triangles always, as you can see, so they are called pseudo triangles. So in both these cases, we see that if you just start with the observation that, even if we started with just Feynman diagrams, which existed, then we would always have these topological structures which emerge. So this is what the first thing that we start with. Now, what is quite surprising, I would say, is that set of all triangulations, linear triangulations of any n-gon can be glued together in a very beautiful combinatorial object, which is, I think, known to many of you. It's called the associahedron or a Stashev polytope. And if you have n-gon, then the dimension of this object is always n minus 3. So I just give you 3 examples. So if you have a 3-gon, then you just get a 0-dimensional polytope. If you have a 4-gon and you triangulate, you can triangulate it in 2 ways. And so you get a 1-dimensional associahedron where the 2 vertices are labeled by the 2 possible triangulations. And similarly, you get a pentagon if you triangulate a 5-gon. And rather remarkably, this is true even for the pseudo triangulations where you triangulate the 2n-gon with a hole in the middle. And all of them can be glued together in a kind of a combinatorial object, which is in fact a polytope which has been discovered fairly recently. And we just call it d hat n polytope for reasons which I unfortunately won't have time to go into. And this is one example where you see that if you just start with like a n equal to 2, so that if you unfold it, you get a 4-gon, and then you did all possible pseudo triangulations, and they can be glued together. And the only thing I want you to keep in mind is that the 2 adjacent vertices I related by what we would call mutation, where we keep all the lines fixed except one. So we can, as you can see here, we can flip this arc, which is on like kind of making the eye into this arc. And that one flip is what is called a mutation. And it is, I would say, a bit non-trivial fact that for any n, these rules are consistent and they form a coherent geometric object in both these cases. And these are really, they are what some mathematicians call mythical polytopes, because they have very surprising properties which we don't generically see for polytopes. So one of the properties is, which is perhaps not that surprising, is that every vertex of, let's say, the associahedron is always adjacent to the dimension of the, is always adjacent to the number of faces which is equal to the dimension of the associahedron. So if I take, for example, a 3-dimensional associahedron, which is obtained by triangulating a hexagon, as you can see that each of this triangulation is like one vertex, and it's adjacent to 3 of these vertices here. And similarly, any codimension K boundary of the associahedron will always factorize into associahedra. So this is a fairly non-trivial fact in the sense that, so if you, for example, take any face, any 2-dimensional face of the associahedron, it can only be either a square or a pentagon. It can never be a hexagon, because we know that the 1-dimensional associahedron is a square, is a line. So the product of 2 lines is a square, and a 2-dimensional associahedron is a pentagon. So these are the only 2 possibilities if you look at 2-dimensional boundary of any associahedron of any dimension. But okay, you may say that this is just simple combinatorics, and how can we go from such bare combinatorial structures to the S matrix? Because to have S matrix, we need dynamics. But in fact, it turns out that there is a kind of a discrete dynamics which is built in the definition of these polytopes, and it is precisely this mutation rule. So this is, just to recall, this is what we mean by mutation, that if I give you a triangulation, I keep all the other chords fixed and I just flip one of the chords. There's only one way I can flip it if I keep everything else fixed, and that flip is what is called a mutation. But okay, if I want to understand this as some kind of a evolution or a dynamical rule, I have to tell you what is the configuration space in which this dynamics is implemented. And so there's an obvious dynamical system that we can define on which these mutation rules are evolution. So in the case of the associahedron, we can say that, well, it's the configuration space is space of all possible chords of the n-gon. And so all possible chords, the cardinality, if you have an n-gon, you can easily check the cardinality of all possible chords is this one. And so I can just look at a Cartesian space of this dimension, and I'm just denoting the coordinates of this Cartesian space with xij. So that kind of becomes my abstract configuration space. And I can do the same thing for the type d hat n polytope, in the sense that I look at all possible dissection chords of the 2n-gon, and you can immediately check that the number of possible chords, if you started with an n-gon to begin with, was n square. And so I've just indicated all the chords here. And just to illustrate this notation, if I don't have any bar here, it's just this linear chord. If I have just one index I here, it's one of these curved chords. And so that's what is indicated. Now the reason there is a xi bar here is because, as you can notice, both the x1 and the x3, they are touching the annulus on the left. But if I started with 1 or 3 bar, and I touched, for example, if I start on 1, and I look at the curve which is touching the annulus on the right, then clearly that's not topologically equivalent to this one. So that is what we would have been called xi bar. So these are the configuration spaces that we kind of are given once we start looking at these dissections. But you may wonder, where are we going? Because we are kind of nowhere close to physics. And at this stage, it is important to note that the relationship with the S matrix is simply rather tenuous, in the sense that, okay, we know that vertices of these polytopes are in one-to-one correspondence, or they are dual to cubic planar graph, but there's nothing more there's no other connection that we have right now. But I would just like to give you one analogy which may be useful, is that the x coordinates that we have defined, which are simply this labeling of the chords, if you now go back to the Feynman diagrammatic just to have an intuition, you can check that each of the red chord is basically capturing the propagator which has this structure. And so that means, just as an analogy, whenever I write small xij, and if you want to have a physics intuition, you should think of the small xij as the specific, a particular Mandelstam invariant for a planar diagram. And similarly, if I wrote, for example, the x1, which was this specific dissection, and if you draw a Feynman graph dual to this, you would immediately notice that the corresponding propagator will be like 1 over y1, where L is the loop momentum. So this is just so that we have some connection, at least some spiritual connection with physics. Okay, but now those are the mutation rules and the configuration space, and you can ask what are the equations, and this is a work of a lot of mathematicians and physicists, and I'm just giving you the final result because of the lack of time, and these equations are remarkably simple to define. So the idea is the following. Suppose we are in the case of the associahedron, so we have an n-gon that we are triangulating. So you just fix any triangulation of the polygon you started with, or if you were in this 2n-gon with a puncture, you fix any pseudo-triangulation. And now the mutation rules give you the following set of equations, that if you define, for example, for the case of polygon, a linear combination of the x variables, they're fairly easy to define, then all the yij's which are not in the reference that you fixed, they should be negative constants. These are the rules that the mutation most naturally give you. And so I have denoted ij collectively because these are the same set of equations which are true whether you are in the first case where you have a polygon with triangulation or the second case where you have the pseudo triangulation. But it's important that there's a universality to the class of equations that we get. So for the associahedron, what is quite surprising is that in fact these equations were derived by some beautiful physics arguments by Nima, Bai, Song, and Yan, and that's why they are known as ABHY equations. But they were in fact later integrated into in mathematics in pure representation theory and representation theory of a class of algebras which are called gentle algebras. So the whole thing could be thought of as really just a math construction where so far we could just forget about the S matrix altogether. These equations then later derived by Nima and collaborators for the pseudo-triangulation, same equation. So overall, we now know that these are the equations which give us the dynamical system for both the associahedra and the type D hat n polytope. But we are still not close to S matrix. But here is a kind of a striking, probably the most important result, that no matter what reference you start with for the triangulation or the pseudo-triangulation, and no matter what positive constants you start with, any like completely arbitrary, the solution to these mutation equations always generate convex realizations of these combinatorial polytopes. And these convex realizations are always sitting in the positive quadrant of the space that configuration space that you started with. So you have this configuration space, which is some dimension for the associahedra and some higher dimension for the the D hat n polytope. And you just look at the positive quadrant and you can always find solution to these equations for any choice of positive constant C, and they give you convex drawings of this associahedra. So these drawings have come simply from the combinatorics, and we haven't put really any input in making these drawings. So I just give you one example. If I go too fast here, that we can take the case of, let's take a reference to be the following triangulation. So this is my reference chord dissection. And then you can check immediately that the resulting drawing would always lie in the positive quadrant, which is spanned by these coordinates. So you don't even have to look at the full configuration space. It is always lying in the space which is spanned by a subset of coordinates. And that is kind of clear because of the fact that the dimension of the associahedron is lower than the dimension of the full configuration space. So this is one example of the two-dimensional associahedron that these mutation equations give you, the ABHI equation give you. And these are really unique realization in the sense they were not found by mathematicians before Nima and Song and collaborators discovered them. They have some interesting properties that precisely if it's a n-3 dimensional associahedron, so let's say this is a two-dimensional associahedron, precisely two pairs of faces are parallel to each other. And one is like at an angle. And this phenomenon remains true in any dimension. So here I give you an example of a three-dimensional associahedron, and you can check that precisely three pairs of faces are parallel and others are at some angle. This is an example of the D hat 2 polytope for the n equal to 2 case, which I have drawn here, which has this. So again, two faces are parallel here, as you can see, and then this I have drawn it a little bit wrong. I mean, this should be not all the faces parallel in this case. Okay, so now we have these positive geometries, and they are in the positive domains of this configuration space, as we saw. And these geometries actually have a striking property, which is really a result, I think, in algebraic geometry, that they induce, and in fact, they are, if we didn't know anything about them, they are in fact defined by a unique form whose rank is same as the dimension of the geometry. And this form has to satisfy some technical conditions, namely that it should have simple poles on all the boundaries and only on the boundaries of this polytope. And because any boundary of the associahedron is a lower dimensional associahedron, the residue of this form should be the form on that associahedron. So there is a recursive definition of these forms, and they are unique for any positive geometry. So there is a unique form for associahedron and also for the D hat n polytope. And so I just give you two examples here for the associahedron case. So this is the unique form that you would have on the one-dimensional associahedron, and this is the form that you have on the two-dimensional associahedron. So this is the form that is induced on this associahedron here. And as you can check that now you start seeing some connection with S matrix, because this function which multiplies the basis is sum over all possible triangulations. And as we know that each triangulation is dual to a Feynman graph, we are somehow getting contribution over all Feynman graphs. So, this looks maybe a bit simple for 5-particle case or this 2-dimensional case, but in general, as you can imagine, we are kind of getting some over all diagrams in one shot in some sense. And the interesting thing is that you may worry that, to do this, we have to fix a reference, but you can check that if you change the reference, the only thing that changes is the choice of this basis. I have 5 minutes. Okay. Which is not surprising because this is sum over all triangulations, and so, that sum could not change even if you change the reference, because you are democratically treating all possible triangulations. Okay, so let me just now say where we are heading, and then we just start looking at the results that we get in physics. So we started with a topological observation that tree-level or one-loop planar graphs, are dual to dissections. This is a fairly harmless, innocuous observation. But then it turns out that this set of dissections define a dynamical system for us, or more precisely, class of algebras, whose corresponding equations, generate a specific class of realization of the polytopes. And this, once we have them, for free, we get these canonical forms which satisfy some technical conditions that they should have poles only on the boundaries. And now it turns out that these forms are what we want to look at, and they define a planar S matrix, for a large class of theories which are, scalar quantum field theories where scalars have colors, and so they are, usually called bi-adjoint scalar quantum field theories. So it's important that here, when I say planar, we may worry we are in large N, but there is no large N. The price to pay is that we have to have color ordering, and so the S matrices we get most easily are where the scalar, where the particles are bi-adjoint scalars. So they have two color indices. And so as you know that, once we fix both the color orderings, then only planar graphs will contribute, like exactly what happens in the large N case. So now let me just quickly tell you how we get how we go from the form to the S matrix. So these x's are the configuration variable. I will go a bit fast here. In the embedding space, I denote it by a vector because it's a large set of coordinates which live in this space or this space. And we know that if you look at the physics Mandelstam space, then it can be coordinatized by the Mandelstam invariants, which I have just denoted as x13, x14, which are just, so when I say x13, it's p1 plus p2 square, for example. So, there are specific Mandelstam invariants which coordinatize the kinematic space of S matrix. And okay, there's a technical assumption here that we are assuming that for this to be the basis of the Mandelstam, the spacetime dimension is always larger than the number of external particles. Otherwise, there are complicated relations between them. So just for lack of time, I will just assume it now. But there is some interesting progress in this direction in this very beautiful paper. And we will assume for the rest of the 3 minutes that all the external particles are massless. And this is really not a restrictive assumption. This is simply because of the lack of time. So, okay, we can say that, well, we have this x, topologically, the small x and capital X are very closely related. So we can ask, okay, it's very natural for us to consider a class of diffeomorphisms between the configuration space and the moment kinematic space. And we can show the simplest possible diffeomorphisms, which are linear diffeomorphisms. Okay, but these are still quite complicated. We can even start with a simpler one that we only look at diagonal diffeomorphism. So we can think of this group, this element G to be just a diagonal of GLN, and M's are some constants. So these are very simple class of transformation we can look between the small x and the capital X. And once we do that, we start getting interesting results immediately. So the first result, which was analyzed by ABHY in their paper, was if you just take the group, this transformation between the configuration space and the kinematic space to be identity, and this M's to be 0, then you immediately get the massless bi-adjoint tree-level S matrix. But you can do something more complicated, and you can look at a transformation, which the details are not important, where this is a transformation. It's some fairly simple transformation. And if you now look at the form, it gives you the perturbative contribution to the S matrix in this theory, where all the external particles are massless and all the propagators are massive. So you see that, it's the same form and the same polytope which gave you, interesting amplitudes, even with a very limited class of mappings between the configuration space and the kinematic space. Okay, I don't have much time, but I will just tell you that you could now be a little more ambitious and ask, like, what if I look at this kind of couplings where I have two scalars, and there is a cubic coupling for the massless case, and there is a cubic coupling between, say, the massless and the massive. And I'm interested in looking at the amplitude contribution to order lambda 2 square. So I'm interested in looking at contribution of all the graphs which have at most one massive propagator. And it turns out that there is an interesting class of mappings that you can define between the configuration space and the kinematic space, such that if you push forward this canonical form, you immediately get this amplitude up to this order. And these structures are really universal in the sense that you can do the same thing for this type, this d hat n polytope, and you can check again that, for example, in the case that I just discussed here previously, if you do this, there is a class of very simple linear mappings which will push forward. Okay, I just finished 1 minute. To produce one loop integrand of this theory up to order lambda 2 square. Okay, just the last slide, that it may appear that, we are only dealing with cubic interactions, but what if I was interested in S matrix of say 5-4 theory, for example? But we know that the set of poles of any higher point scalar interaction is a subset of the set of poles with cubic vertices. So it turns out that, and indeed it turns out that because of this basic fact, the polytopes we obtained, in fact, naturally generate S matrix in any phi to the p theory by an operation that in mathematics literature is called projection, which was discovered by these two mathematicians. I just give you a picture here. So this is a three-dimensional associahedron. And now the idea is very, very simple. If you look at any subspace of your configuration space, for example, if you take 1, 4, and 1, 6, and look at all the equations which only involve 1, 4, and 1, 6, then what you get is a lower dimensional polytope, which is a projection. And these polytopes are what are called accordiahedra in the math literature. And it turns out that these projections immediately start producing for you. So I give you two examples here, and they produce for you some amplitude in bi-adjoint phi to the 4 theory. And when one can do more complicated analysis like this. Okay, so this is the final shot that we have a universal polytope at for tree level and one loop integrand, which is the the ABHY associahedron, for example, at tree level. And all we have to do to get different S matrices is either a diffeomorphism or a projection. And so that this is a summary of everything I try to discuss. And that you can ask, okay, how did we get unitarity and locality here? And the fact that these associahedra have interesting boundary structure gave us unitarity, and the form, the canonical form at the simple poles gave us locality of the S matrix. So I end here, and analytic structure of S matrix has also influenced writers, literary writers, and this is the quote. So thank you very much.